In this section, we'll learn a little bit about the chemistry of acids and bases. What does it mean to say something is an acid or a base? Well, actually, there's a lot of different ways to define what an acid is and what a base is. The different definitions are used in different areas of science and different branches of chemistry. One of the easiest definitions, and one of the ones that's most widespread as a result, is what's called the Arrhenius definition of acids and bases. In the Arrhenius definition, we say that any compound that produces hydrogen when placed in water is called an acid. Essentially, this means any substance that dissociates into a hydrogen ion and another substance can be called an acid. Something like hydrochloric acid, HCl, dissociates into hydrogen ions and chloride ions. Because it dissociates into hydrogen ions, we call it an acid, hence the name hydrochloric acid. In the Arrhenius definition, a base is any substance that produces hydroxide ions when placed in water. Hydroxide has the chemical formula OH-, and it's a polyatomic ion. An example of a base by the Arrhenius definition is the substance sodium hydroxide. NaOH dissociates into a sodium ion and a hydroxide ion in water, hence the reason we call it a base. In fact, there's only one substance that is both an acid and a base by the Arrhenius definition, and that substance is water itself, or H2O. The reason is, as we've seen previously, H2O molecules can dissociate. When they break apart, water molecules don't break into two hydrogens and one oxygen. They break into a hydrogen ion and a hydroxide ion. Because water is capable of dissociating into 1 part hydrogen ion and 1 part hydroxide ion, it's both an Arrhenius acid and an Arrhenius base. The Arrhenius definition of acids and bases is really simple, but it also has some limitations. For one, the Arrhenius definition is limited to aqueous solutions because the definition revolves around how compounds act in water. Another shortcoming of the Arrhenius definition is that while some acids and bases are easy to recognize simply by the presence of hydrogen or hydroxide in the chemical formula, there are substances that can produce hydrogen or hydroxide without actually containing those ions. In fact, one very common substance, ammonia, reacts with water to produce hydroxide ions, even though ammonia's chemical formula, NH3, does not contain hydroxide itself. For this reason, many chemists don't actually use the Arrhenius definition when working with acids and bases. They use one of a number of other definitions. The definition that is most common with chemists that work in the realms we study in general chemistry is what's called the Brønsted-Lowry definition. The Brønsted-Lowry definition revolves around the hydrogen ion alone and how it acts with different molecules. Basically, the Brønsted-Lowry definition of acids and bases revolves around a hydrogen ion being traded between two molecules. We say that the acid is the compound that starts out with the hydrogen and donates or dissociates from it. So acids are compounds that are capable of donating hydrogen. The base is the compound that's capable of accepting that hydrogen ion. So in a Brønsted-Lowry reaction, the acid loses or dissociates from the hydrogen ion while the base accepts it. This is a more general definition, and this is why some people prefer the Brønsted-Lowry definition to the Arrhenius definition. We already said that water is an example of both an acid and a base by the Arrhenius definition. But this is actually also true by the Brønsted-Lowry definition. Water is a Brønsted-Lowry acid because, as an acid, it should be able to donate hydrogen ions. Well, we've already seen that water can dissociate into a hydrogen ion as well as a hydroxide ion. The fact that it dissociates and produces hydrogen ions makes it both an Arrhenius acid and a Brønsted-Lowry acid. But what about a Bronsted-Lowry base? A Bronsted-Lowry base is a compound that accepts or gains hydrogen ions. Water is capable of gaining or accepting a hydrogen ion. When H2O bonds with H+, the new compound that's formed has the chemical formula H3O positive. It has 3 hydrogens, 1 oxygen, and a positive charge. This is better known as the hydronium ion. The reason this is significant is not just that it means water is both an acid and a base by the Bronsted-Lowry definition, but it also explains a little bit about what happens at the molecular level in any sample of H2O. Liquid H2O is mostly molecules of H2O, but on a very, very small scale, some H2O molecules are breaking up. As they do that, they produce hydrogen ions, which react with water to make hydronium, and hydroxide ions. This is one reason that even pure water can still conduct electricity, because it still contains ions. The other reason this matters is that the hydronium ion is present anytime water and hydrogen are mixed together. Again, here we're speaking about the hydrogen ion specifically. The reason this matters is that you can use the term H3O+ interchangeably with H+ in many different chemical formulas and equations. In your textbook, you'll notice that some equations appear with H+, while other equations appear with H3O+. Numerically, they're the same thing. Sometimes we write H+ because it's simpler, and sometimes we write H3O+ to be more realistic about what's actually happening. Whether you choose to use the hydrogen ion or the hydronium ion in equation generally won't make a difference in this class. So if there's all these different acids and bases out there, and in particular Bronsted-Lowry acids and bases, how can we recognize them on paper? We know that Bronsted-Lowry acids are compounds that donate hydrogen. So the first thing to look for is whether a compound has hydrogen to begin with. But just having hydrogen doesn't guarantee that you're looking at an acid. Not all hydrogen in a molecule are capable of leaving or dissociating from that molecule. We call this acidic hydrogen. So not all hydrogen in a molecule are acidic. For instance, we've seen previously the chemical propane, which has the chemical formula C3H8. Those 8 hydrogen, while they are hydrogen, actually don't ever leave that molecule. They don't dissociate from propane when placed in water. This is why propane is not an acid. Meanwhile, a compound like ascorbic acid, which is an important part of vitamin C, contains hydrogen ions that do dissociate, hence the reason it's an acid. So why is it that the hydrogen in propane don't dissociate or leave the molecule, while the hydrogen in ascorbic acid can? Well, this actually delves into a very deep topic in chemistry that we really don't have time to explore in depth. But what you will notice is that most acidic hydrogen are bonded to electronegative atoms. In the molecule propane, the hydrogen are directly bonded to carbon. Carbon isn't terribly electronegative, and for this reason, it's unlikely the hydrogen will leave the carbon unless a chemical reaction is taking place. In ascorbic acid, however, we have several hydrogen that are bonded to oxygen. Oxygen is fairly electronegative. What this means on an atomic level is the oxygen is capable of taking electrons from the hydrogen and allowing the hydrogen to dissociate from the molecule as H+. Because electronegative atoms are able to do this, many acidic hydrogen, or many acids in general, contain electronegative atoms with hydrogen bonded to them. Another way to notice when you're looking at an acidic compound is if you're looking at a chemical formula and the hydrogen is listed separately, or if just 1 or 2 hydrogen are listed separately from the other ones in the molecule. A good example of this is a compound we've seen previously this quarter, CH3CO2H. This is acetic acid, and one of the giveaways that it's an acid is that one of the hydrogen is written at the end of the compound instead of being grouped with the 3 hydrogen in the middle of the compound. The reason acetic acid is not written CH4CO2 is that one hydrogen is acidic. It's able to leave or dissociate from the molecule. So if you see a hydrogen written at the very beginning or the very end of a molecule separate from the other hydrogen, it's a good indication you're looking at an acid. There's also some easy ways to recognize Bronsted-Lowry bases, although generally we'll see that they're not considered to be as significant in general chemistry. Bronsted-Lowry bases tend to have a lone electron pair. That means when you're looking at the Lewis structure, you'd see 2 dots. These 2 dots, or 2 electrons, are able to bond with the hydrogen ion, allowing the molecule to accept it. One other aspect to consider about acids is that some acids are able to donate more than one hydrogen. Let's look at ascorbic acid as an example. Notice that of all of the hydrogen in ascorbic acid, 4 of them are bonded to electronegative oxygen atoms. Because these 4 hydrogen are all bonded to electronegative atoms, each one of them has the potential to be acidic. This is what we call a polyprotic acid. Poly means many, and protic refers to the proton, or hydrogen ion. A polyprotic acid is an acid that can donate more than one hydrogen. Occasionally you'll also hear more specific terms like diprotic or triprotic. That simply refers to precisely how many hydrogen can be donated. But it's important to realize that acids can donate just one hydrogen, or sometimes they can donate more than one. Once we've learned how to recognize acids, it is important to consider that not all acids are created equal. In other words, while all acids, according to the Bronsted-Lowry definition, donate hydrogen, some do a better job of donating hydrogen than others. Acids that always donate their hydrogen 100% of the time are what we call strong acids. So an example of a strong acid is something like hydrochloric acid. Hydrochloric acid donates hydrogen every time. An acid that doesn't always donate its hydrogen is what's called a weak acid. Acetic acid is an example of a weak acid because that hydrogen that's donated in acid-base reactions isn't always donated. In other words, you might have 1,000 of those molecules, but only a handful of them will actually donate their hydrogen. The fact that donation can occur makes it an acid, but whether it occurs all the time or just part of the time dictates whether you're looking at a strong acid or a weak acid. It's important to realize that the terms strong and weak are different than the term concentrated. When we talk about a concentration, we're talking about the number of acid molecules in a volume of liquid. It doesn't necessarily mean whether or not those molecules will always donate their hydrogen ion. So while you can have strong, concentrated hydrochloric acid, you can also have diluted hydrochloric acid. It would still be a strong acid, but it wouldn't be in a very concentrated form. Acid strength is quantified using a modified version of the equilibrium constant we've seen earlier in this course. You may recall that the equilibrium constant is how we define whether a reaction favors reactants or products when it's at equilibrium. What we learned previously is the equilibrium constant is found by looking at the concentration of the products at equilibrium compared to the concentration of the reactants. When it comes to acids, the reactant is the acid. The product is simply the acid after it's dissociated from the hydrogen ion. Because of this, there's a special type of equilibrium constant called the acid dissociation constant, or Ka. To find the Ka, we simply look at the ratio of dissociated acid, or the acid that has already lost its hydrogen, to the amount of acid that still retains its hydrogen, basically the acid in its original form. If all of the acid dissociates, that means we have a very large numerator, and the consequence is that we end up with a very large value of Ka. Ka's for strong acids tend to be very large, much, much greater than 1, because the numerator is so big compared to the denominator. Usually we're talking about values in the thousands. Meanwhile, if you're dealing with a weak acid, it means that you might have only a small amount of dissociated hydrogen compared with the original form. Because of this, when a Ka is less than 1, a fraction or a decimal, that's how we know we're looking at a weak acid. Let's look at the Ka's of some common acids to illustrate this point. We already mentioned hydrochloric acid, which most people have heard of. Hydrochloric acid is a strong acid because it dissociates almost completely into hydrogen ions and chloride ions. Consequently, its Ka value, or acid dissociation constant, is a very large number, about 1 times 10 to the 7th. Sulfuric acid is also a very strong acid, and we can tell that by its Ka, which is about 1,000, or 1 times 10 to the 3rd. Let's compare those with some weak acids. Acetic acid, which you may remember is the compound found in vinegar, has a Ka value of 1.8 times 10 to the negative 5. That's a decimal value, or a number smaller than 1. That tells us that acetic acid is weak, or in other words, that the hydrogen on acetic acid only dissociates from the compound a fraction of the time. Similarly with ascorbic acid, which is associated with vitamin C, the hydrogen in ascorbic acid dissociates a fraction of the time as well, because its Ka value is 7.9 times 10 to the negative 5, again a value less than 1. The Ka values are available for just about every acid you can think of, and they're not something you're expected to memorize. Ultimately, though, what we usually look at when we're trying to gauge the strength or the concentration of an acid is the pH of the solution it's in. And all the pH is, and actually where the name itself comes from, is from the concentration of hydrogen in the solution. The higher the concentration of hydrogen, the lower the pH of the solution. So if we think about a strong concentrated acid, something like sulfuric acid, battery acid, hydrochloric acid, the strong concentrated acids will tend to have a hydrogen ion concentration that's around 0.1 moles of acid per liter. That's a very rough estimate. They could be bigger than that, they could be smaller than that. But let's compare that with a strong concentrated base. A strong concentrated base has very little hydrogen in the solution. In fact, if we measure the amount of hydrogen ions in solution, a strong concentrated base might have as little as 1 times 10 to the negative 14th moles per liter. That's 0.00000, etc., 1 moles per liter. This is one of the reasons that the pH scale was created. Can you imagine if you were measuring the pH of a solution and you had to give the hydrogen ion concentration to say that the pH of stomach acid is something like 0.01 and then the pH of your bleach solution is 0.00000000000 something? That would be really inconvenient. So the pH calculation was devised to deal with the fact that we can get very, very small numbers when working with hydrogen ion concentrations. And to deal with that, we use the mathematical function called the log. The log is a function, meaning it's something that we do to a number in order to elicit a result that's helpful to us. What the log does is it essentially allows us to get rid of all those zeros that take place in these tiny little numbers. Now, how you're going to calculate the log is how you're going to calculate the pH is by taking the negative log of your number. This depends on your calculator for exactly how you're going to do it. So make sure you have your calculator in front of you, and let's look at how we could calculate the pH of these solutions. With your own calculator, let's first calculate the pH of a strong concentrated acid that has a concentration of 0.1 moles of hydrogen per liter of solution. Again, the actual equation is that the pH is equal to the negative log of the hydrogen ion concentration. So if our hydrogen ion concentration is 0.1, my pH is the negative log of 0.1, and I need to use my calculator to solve this for a number. To do this, or how you do this, depends on exactly which calculator you have. About 50% of you are going to have calculators where you want to type things in the following order. First, you want to press the negative sign. The negative sign, or your negative button, is different than the subtraction button. Press your negative sign and then find your log button and press that. Notice we're not entering any multiplication signs, addition signs, or anything else. After pressing your log button, this is where it's time for you to enter the number. In this case, our concentration of hydrogen ions is 0.1, so I'm going to enter 0.1. At that point, press equal. If your calculator works in this order, it should give you the answer 1. The pH of a solution that has a hydrogen ion concentration of 0.1 would be 1. If you got an error button, an error notice or some other thing happening to your calculator, try entering everything in the reverse. So first enter 0.1, then press your log button, and then press the negative sign. You might have to play around with your calculator to get it to work exactly right. Some will require parentheses, and each has its own particular order it wants to go in. But you need to make sure that you can work your calculator before you can use this on an exam. Let's do another example. Actually, let's do a couple more so we can make sure you know your calculator is working correctly. Let's do the same thing, but now let's calculate the pH for a strong concentrated base that has a hydrogen ion concentration of 1 × 10 to the negative 14. Again, we're still going to take the negative log of 1 × 10 to the negative 14. How you enter 1 × 10 to the negative 14 really depends on how comfortable you are with your EE or exponent button. But again, make sure you enter it in the order that your calculator requires. You may enter the negative sign, then press the log button, then enter 1 × 10 to the negative 14, or on other calculators, you might enter 1 × 10 to the negative 14, then press log, then press the negative sign. When you do that, you should end up with the result 14. The pH of a solution that has 1 × 10 to the negative 14 moles per liter of hydrogen ions, the pH would be 14. Let's do one more. No matter what the concentration is, you can always use the same equation to calculate the pH. So let's say we have a solution that's not 1 something. It has a hydrogen ion concentration of 0.035. Again, use the pH expression and what you've learned about your own calculator to calculate this value. Take the negative log of 0.035. Go ahead, pause the video and try it yourself. The answer you should acquire is 1.5. So in a solution that has a hydrogen ion concentration of 0.035, that's 0.035 moles per liter, I would have a pH of 1.5. So what does it mean for a substance to have a pH of 1.5? Well, aside from telling us exactly what the hydrogen ion concentration is in that substance, it also allows us to put it on the pH scale. Traditionally, we think of the pH scale as starting off with the number 7. 7 is exactly in the middle of the pH scale, and it's what we refer to as neutral. You may already know that one of the substances that has an exactly neutral or completely pH 7 is totally pure H2O, completely pure water. Below a pH of 7, we have solutions that we classify as acidic. So these are acidic solutions or acids. While we usually think of the pH scale as going as low as 1, there are strong concentrated acids out there. An example would be battery acid, which actually have pHs even lower than 1. Some strong concentrated samples of battery acid can even have a negative pH. Above a pH of 7, we have basic solutions. And again, traditionally we think of these as going as high as 14, although they can go higher. So the pH scale is traditionally thought of as going from 1 to 14 with neutral solutions in the middle. Now on the pH scale, we can put virtually any substance. In the human body, for instance, we might think about stomach acid, which traditionally has a pH of around 1 to 2. The exact pH depends on your genetics, what you've eaten, and other biological considerations. There's many of things that you probably eat that also fall on the acidic side of the scale. Different types of soda tend to have pHs around 3 or 4, depending on exactly what type of acid they contain. Coffee, beer, and wine all has slightly higher pHs, around 5 to 6. Rainwater is actually slightly acidic, even in its most pure form, because of the way it interacts with carbon dioxide as it falls through the atmosphere. So rainwater usually has a pH of around 5.5 or 6. If it goes below 5.5, we refer to that as acid rain. Not all environmental water, though, is neutral or acidic. In fact, ocean water is close to a pH of 8. And in other basic solutions, not surprisingly, one thing you'll find are antacids. Antacids are just bases that are designed to react with the acids in your stomach. They can range in pH from around 8 to 11, depending on their strength and concentration. Beyond 10 or 11 on the pH scale, mostly what you would be familiar with in this range are things like cleaning agents. Ammonia and bleach are both very high on the pH scale. But again, everything can be put on this scale. And you can even back calculate based on pH what the original hydrogen ion concentration of that substance is. To calculate the amount of hydrogen ion, if all you know is the pH, you simply take the number 10 and raise it to the negative pH. So water, if it's pure and neutral with a pH of 7, has a hydrogen ion concentration that is 10 raised to the negative 7th, or 10 to the negative 7th. So far we've looked at the idea that acids donate hydrogen into solution, and the more hydrogen ions in solution, the lower the pH of that solution can go. But what's left over after an acid donates its hydrogen? Or for that matter, what happens to a base after it accepts hydrogen? Well, after the acid has done its thing, and after the base has accepted its hydrogen, we say that the form that remains is what's called the conjugate form. And again, this depends on whether you're talking about an acid or a base. Acids donate hydrogen, so the remaining molecule essentially has picked up a hydrogen, and it's what we call the conjugate base. Let's think about the general formula HA for an acid. When HA loses a hydrogen ion, the molecule that remains, or the atom that remains, is simply A. Because HA was neutral and we've separated a positive charge from it, A must be negative. You can also think about the fact that if you ran these backwards, the positive and the negative charges would cancel each other out. Let's look at a more specific example. Hydrochloric acid dissociates or donates a hydrogen ion, and the molecular atom that remains is chloride with a negative charge. This is what's called the conjugate base of hydrochloric acid. So the conjugate base is simply a compound that can act like a base if we run the reaction backwards, but mostly it exists because it's what's left over after an acid donates a hydrogen ion. And it's easy to predict the chemical formula. To write the chemical formula for a conjugate base, simply remove one hydrogen from the acid and decrease the charge. Earlier today we saw the example of CH3CO2H, which is acetic acid. Again, the hydrogen is written separately in the formula, which clues us in on the fact that it's an acid. So as an acid, it donates a hydrogen ion. Take a moment, if you'd like, pause the video, see if you can write the chemical formula for the conjugate base of acetic acid. To write the chemical formula, I simply remove hydrogen and adjust or decrease the charge. So after removing hydrogen from the formula, I have CH3CO2 because I just removed that one hydrogen from the end, and I have to adjust the charge. Since it started neutral, I'll make it negative. Acids donate hydrogen, leaving behind the conjugate base, and the opposite can be said for bases. Bases accept hydrogen, so what they leave, or what results from that process, is called the conjugate acid. So for any base B, when it accepts or gains a hydrogen ion, your new formula is B with the hydrogen and a positive charge. If we wanted to do that for a specific example, we could choose something like the base ammonia. When ammonia accepts a hydrogen ion, it changes the chemical formula as well as the charge. To write the conjugate acid, I simply join the two together. Instead of NH3, I'll now have NH4, and it's positively charged. So just the opposite of what we did to write the conjugate base, we have the conjugate acid, which you get simply by adding a hydrogen to a base and increasing its charge. While this may seem like it's not all that important, we'll be seeing later that the balance or the equilibrium between base and conjugate acid, or acid and conjugate base, is one of the most important aspects of understanding how real-life aqueous acid-base solutions work.